All right, guys. So we're finishing up this here, 2.1, because we split it up so that we could kind of go over 2.2, so that y'all could see those do that. That's it. We're not doing anything else with 2.2. Not anything in that type. You're not going to have to verify any other equations from here on out, especially on the test or on the review sheet. Because it's nice to know how to manipulate the equations, but that's about it. Because we will still be using those kind of manipulations, especially with solving and trying to work with them and rewriting the equations in a better way to help us be able to solve. Now, for this one here, we want to solve using the given information. So they tell us that x is equal to 2 times tangent of alpha, where alpha is between 0 and pi over 2, so 0 and 90 degrees. And we want to solve this here, square root of 4 plus x squared. So really what we're starting off with is the square root of 4 plus x squared. Now, even though they do look a little different, the x and x equals 2 times tangent of alpha, and the x in this equation here are the same. For some reason, the program decided to write it as capital X when I was putting it in, but they are the same. And so what we're going to do to solve this as well, I'm going to replace x squared with 2 times tangent of alpha. And luckily, because there's not a plus sign between the 2 and tangent, we're just multiplying it by itself. So what we can say is that we have the square root of 4 plus 2 squared is 4 times tangent squared of alpha. Because it's nice when it's just a single term, because even though we have 2 times tangent of alpha, it is just one term. So when we square it, we're just multiplying it by itself, or we're just squaring each individual term. So the 2 squared and tangent squared. Now we get this here, yes? Now we know that the 4, we can take the square root of it, yes? Now the only way that we could take the square root of 4 plus 4 times tangent squared is if I could rewrite it as a single set of parentheses squared, and then they would simplify out. But to simplify this, one of the first things we can do is factor the 4 out. And if I factor the 4 out of 4, we're left with 1 plus tangent squared of alpha. Now taking the square root of 4 is quite easy. We like that because square root of 4 is just 2. Yes? But the other part that we have is this here, this 1 plus tangent squared of alpha, yes? What is 1 plus tangent squared of alpha the same as? I believe it is secant squared, but I'd go on and check to make sure. Because as we have by definition, 1 plus tangent squared of alpha is equal to secant squared of alpha. We also have that 1 plus cotangent squared of alpha is equal to cosecant squared of alpha. Because these are just our trigonometric or our Pythagorean identities. And these here again do come up a lot. And the other one we have is sine squared of alpha plus cosine squared of alpha is equal to 1. And we can manipulate these in any way. Because if we needed, say, instead of having 1 plus tangent squared of alpha, we had secant squared of alpha minus 1, that's the same as tangent. Because we could also say that tangent squared of alpha is equal to secant squared of alpha minus 1. We could rewrite these in any way, shape, or form to get it to work with what we have. Now this problem is essentially done Because what we have is the square root of 4 times secant squared of alpha, yes? Well, we could take them individually. The square root of 4 is 2. Square root of secant squared is secant of alpha. And that's it. So even with going on from this here, we won't do any of the verifying. Knowing how to manipulate these properties is going to be helpful. Now, the reference sheet I gave you, the first kind of main 3 that we have, are very useful in manipulating. The power property, the sum to, let's see here, sum to product, product to sum, our half angle, double angles, power reducing formulas, we're not really going to manipulate those as we do with Pythagorean, where we rewrite them in one way, shape, or form. If we're using those, we're really applying the property or applying that theorem to the formulas, one way or the other. We're going from one side to the other, like we've done with pretty much every theorem you've had up to this point. The Pythagorean identities are really one of the few where we change it to fit what we have and not just apply it straight in. Any other questions on this here? So this one here, x is equal to 3 sine of alpha, and alpha is again between 0 and pi over 2. And we have the square root of 9 minus x squared. So we're starting off with 9 minus x squared. So we're plugging in 3 sine of alpha into this here. Now, what we use is the angle, or what we define the angle as, really doesn't matter for most of these here. Now, for the most part, for trigonometry and above, we use Greek letters for angles. So theta, alpha, gamma. Most of those are used for angles for anything that we're solving. But for the most part, we use alpha, theta, and beta. Those main 3. So alpha, theta, beta are the main 3 that we use for angles. But we could use x or any other one. We normally apply 2 as if we're talking about 2 different angles that aren't going to be the same. So we'll use 2 of the Greek letters. So that's just kind of a side tangent. Now, looking at this here, we'll do the exact same thing we did before. We're going to square 3 sine of alpha, and 3 squared is 9. And we have sine squared of alpha. And again, one of the main things we're wanting to do is to simplify this radical. Well, the first thing we can do is factor out the 9, which leaves us with 1 minus sine squared of alpha. As we said already, sine squared of alpha plus cosine squared of alpha is equal to 1, yes? And again, these Pythagorean identities are the only real ones we're going to manipulate to get what we want. And what I have inside this radical is 1 minus sine squared, yes? Okay, what we can do over here is subtract sine squared of alpha from both sides, which will tell me that I have cosine squared of alpha is equal to 1 minus sine squared of alpha. Really just tells me over here that I have the square root of 9 times cosine squared of alpha. And square root of 9 is 3. Square root of cosine squared is just cosine. So we get 3 cosine of alpha. Questions on this here? We're ready to look at the next part. Because I found those to be not too bad or not too challenging. They're not too overly difficult. Because it's just plugging it in and then simplifying and using our Pythagorean identities to simplify. Now these here, they want us to simplify. So we have two fractions and we want to add them together. Well, if we're going to add any fractions together, the denominators have to be the same. Have to be the same. So sine of alpha 1 plus cosine alpha. Cosine alpha, sine of alpha. Now this here is actually pretty nice, unlike some, especially when we added fractions like 3/4 and 5/9, where we had to try to find the first number that 4 and 9, both the denominators would be the same. Here, well, the one side has 1 plus cosine of alpha, yes? So the other side must have 1 plus cosine of alpha. So we're going to multiply it on top and bottom. The one on the right has sine of alpha on bottom, so we have to multiply top and bottom by sine alpha. And doing this will get us to have the denominators be the same, because we'll have sine of alpha times 1 plus cosine of alpha. Now looking at this here, the denominator specifically, will we have any term where we have sine or cosine to a power? Well, not, I mean in the bottom, yes, on top, because on top we will. Because on the left side we will have a cosine times cosine, and on the left side we will have a sine times sine, yes? But in the denominator, on either one of them, we'll have sine times 1 is just going to be sine. Plus cosine times sine is just cosine times sine, yes? That really doesn't simplify anything at this point. I don't see how we can reduce it. And what I mean by that is especially lining up with our trigonometric functions, our trigonometric identities, our Pythagorean identities, because that's dealing with sine squared, cosine squared, tangent squared, secant squared, cosecant squared, where we have something to a second power. It's squared. Well, the denominator's not going to have that. And we could possibly deal with some of our co-functions, our reciprocal functions, but at this point, because it's not going to help, we don't see any way that it can help. What I'm going to do is leave the denominator as sine of alpha times 1 plus cosine of alpha. I'm going to leave it alone. I'm not going to multiply that out. And I'm not going to multiply it out on the slim chance or the possible chance that something on top is somehow going to simplify either to be just sine or just 1 plus cosine. Because if we have one or the other, then they will cancel nicely here. Unlike if we multiplied them out, where we would end up having to factor it back out to be able to simplify. Like last year in Algebra 2, where we dealt with adding and subtracting rational functions, it's easier to leave the denominator in this factored form than it is to multiply it through. Now that's not going to work every single time, especially if we notice that multiplying through will give us one of our Pythagorean identities, where we're dealing with cosine squared or sine squared or tangent squared, or secant, cosecant, or cotangent squared, where we have something we can replace with one of those. Then we will probably have to use that. But either way, leaving it this here is not a big deal at this point. Now the numerators we can go on and multiply. Sine times sine is going to be sine squared. The other side will have cosine of alpha times 1, which is just going to be cosine of alpha. Cosine times cosine is going to be plus cosine squared of alpha. Questions on this so far? Okay, now we can add them together. If we add these together, we'd have sine squared of alpha plus, I'm going to put cosine squared of alpha next to it, plus cosine of alpha over sine of alpha times 1 plus cosine of alpha. Any questions on how we got to this point here? Did one of our Pythagorean identities show up? I'll give you all a second to write. Look at it. I think one of them did, didn't they? Because what is sine squared plus cosine squared? For in Pythagorean identity, sine squared plus cosine squared is 1, yes? So if I'm wanting to simplify this, we could say that that is just 1 plus cosine of alpha over and this is part of the reason why I didn't want to multiply the denominator. Now we can think of the numerator, because again these two are added, so they are essentially a single term. 1 plus cosine of alpha on top is a single term. And anything divided by itself is 1. So these here are going to cancel out, which tells us that we have in the denominator sine of alpha. And what do we have in the numerator? It would be 1. The only way we can get 0 is by subtracting the same thing from itself. If we're simplifying with division, anything divided by itself is understood to be 1. And a lot of times, especially in Algebra 2 and Algebra 1 and geometry, we have more than one thing on top. So we mark it out, say it's gone, and just leave whatever else is with it there and then kind of move on from there. We don't really emphasize that it's really simplifying to 1. And the nice thing with 1 is whenever we multiply it with something, it doesn't change it. But we have this here, so 1 over sine. And we could say, and I would take this as the final answer, or if we wanted to write it a little bit simpler, because what is 1 over sine the same as? Cosecant of alpha. For some reason I tried to write x, because cosecant is the same as 1 over sine. Neither one of these here work. Questions on this here? We ready for another one? Okay. So we need these denominators to be the same, yes? So what are we going to multiply the 1 on the left by? We'd have 1 in sine of alpha, but it would be 1 minus sine of alpha. And the 1 on the left is going to be 1 plus sine of alpha. We can put the parentheses around alpha, or we can leave them off, which if you are fine with leaving them off, that's fine. I put them in there especially if we have something added, or just kind of making sure that we know that that x or alpha is by itself, that anything added to it afterwards is not necessarily contained within it. That sine of alpha plus 1 is the same as sine of alpha plus 1. These are the same. We're not thinking of it as this here. Does that make sense? A lot of the textbooks will write it like this here, sine of alpha plus 1, and they're talking about sine of alpha in parentheses plus 1. If they meant for it to be alpha plus 1 inside, they'll put parentheses around it. I find that a little bit frustrating because you're having to remember that the alpha and 1 aren't actually together. So a lot of times, especially on the review sheets or test, I will put the parentheses, especially if something's added to it, just as a reminder the alpha is not, and that 1 aren't being added together. Okay. Now we need to multiply these together, yes? Well, luckily for us, the numerators for both actually quite nice. And it hasn't changed since kindergarten. Our still favorite multiplications still consist of two numbers, 1 or 0. Because if we multiply by 1, it doesn't change it. And if we multiply it by 0, it just becomes 0. So those are the two nice ones. Now when we look at the denominator, 1 minus sine of alpha and 1 plus sine of alpha. Those have a little bit of a special property, don't they? They're the difference of perfect squares. Because our difference of perfect squares, a squared plus, or a squared minus b squared is a plus b times a minus b. So these are a difference of perfect squares, which will work out nicely. This is going to be one of our trigonometric identities. So this one here we would multiply out. I'm going to multiply through the one on the left so that we see it, and then I'm just going to copy it over for the one on the right. Because we know that the denominators will be the same, so the multiplication for both will be the same. We don't have to rewrite it twice. So here we have 1 times 1, which is 1. 1 times sine of alpha is going to be plus sine of alpha. Negative sine of alpha times 1 is negative sine of alpha. And lastly, negative sine of alpha times sine of alpha is negative sine squared of alpha. Now for us here, the middle terms are going to cancel, yes? Which just leaves us with 1 minus sine squared of alpha. And really, if you notice that it is a difference of perfect squares, whenever we multiply difference of perfect squares, it's the first term times the second, or first term squared times the second term squared. 1 squared is 1, sine squared is sine squared, and we subtract. Now the last thing, or one of the last few steps, now we can actually add these together. Because on the bottom we're going to have 1 minus sine squared of alpha. On top we have 1 plus 1 is 2, yes? What's negative sine of alpha plus sine of alpha? 0. So the numerator is 2. I would agree that this is more simplified, or a simpler looking than what we started with, yes? But I wouldn't say it's quite simple. It's not as simple as we could get. And the reason I say that is because, well, 1 minus sine squared is the same as cosine squared. I'd say that's even simpler than 2 over 1 minus sine squared of alpha, yes? We can make it even simpler. 1 over cosine is what? Secant, yes? So we could rewrite this as 2 times secant squared. And I say that's even simpler looking than 2 over cosine squared. And that's it. So even though we're not verifying like we were doing, we're essentially still doing the same things. We're manipulating these equations to get them to work better for us. And especially when we start trying to calculate these, knowing these manipulations works for us. Because if I was wanting to evaluate 2 secant squared of alpha for when alpha is pi over 4, I wouldn't plug it in as 2 secant squared of pi over 4. I'd plug it in as 2 over cosine squared of pi over 4. Write it in a way that I can calculate it better. Because as we've seen already, we can't plug, there's not a button that does just secant. We have to use cosine to the negative 1. Not the inverse, but to the negative 1. Questions on this here? Simplify. So we're wanting to just multiply this out. We want to just distribute this out and simplify it if we can. So we're going to distribute cosine of alpha times sine of alpha is just cosine of alpha, sine of alpha. Cosine of alpha times negative cosine of alpha is negative cosine squared of alpha. Negative sine of alpha times sine of alpha is negative sine squared of alpha. Oh, that's so close. And sine of alpha times negative cosine of alpha is going to be plus cosine of alpha sine of alpha. Now you might be wondering why I ordered it with cosine first and sine second. Well, the first one where we multiplied cosine and sine, I put cosine first, yes? So just so that we can see that those two are the same. Cosine times sine is the same as sine times cosine, yes? So I'll just keep them looking the same so that when I'm looking back, or especially when we start simplifying, okay, these are the same and we can go on and add them. Which here it's not too bad to say, okay, we know that they're the same and working through it. On the homework, it might be good, especially just for ourselves, to have them look the same so we can add them. And again, in a no pressure situation, that homework is, okay, we can kind of, okay, I need to flip those around and change it. But especially when we're working on a test, having one of those flip the other way, we might overlook the fact that those are indeed the same, and we can actually combine them. Because really we can say that cosine times sine plus cosine times sine is 2 cosine of alpha sine of alpha. And I did say already that this here is very close to one of our Pythagorean identities, isn't it? Because the ones that we have is what? Sine squared plus cosine squared is 1, yes? Well, both of them are negative, aren't they? Can I pull that negative out? Yeah. Because I could factor the negative out of it, which would leave me with cosine squared of alpha plus sine squared of alpha. Yes? One more. And that's just going to be that's it. If it worked out that the signs had been different, one of them had been positive, one of them had been negative, we really couldn't have used the Pythagorean identity the way we did. We could probably switch one out with the other so that cosine squared is 1 minus sine squared, and then try to simplify it that way. But here, that's our answer. Questions on this here? We ready for the next one? Well, looks like that's it. So, I mean, with most of the multiplication and simplifying, it's not too bad. Multiply it through and see if we can replace with one of our trigonometric identities. So especially with secant, cosecant, tangent and cotangent, see if we can replace either secant with 1 plus tangent squared, or vice versa, 1 plus tangent squared with cosecant squared. But most likely, especially for these here, we'll end up using the Pythagorean. And that is it for 2.1.